AB Calc 3.8 day number 2. I just wanted to run through a couple of examples here. I wanted to start with 1997, multiple choice number 17. You could find this also in your problem set. It says if x squared plus y squared equals 25, what is the value of the second derivative, right? This is the derivative with respect to x of dy dx. Okay, that's called Leibniz notation. Leibniz notation. Leibniz was a mathematician who founded this notation that is equivalent to the second derivative with respect to x. Okay, at the point 4, 3. So we're given the point. We just want to find the second derivative at that point. Okay, so let's take our expression, which is the equation of a circle, okay, with a radius of 5 centered at the origin. Implicitly differentiating, we would get 2x plus 2y times dy dx is equal to 0. Okay, now I'm going to isolate dy dx. You don't have to isolate dy dx, but I am, just so you can see the notation show up to what I've shown you in the beginning of the problem here. So I'm going to subtract 2x divided by 2y, and dy dx ends up equaling negative 2x over y, or excuse me, over 2y, which comes out to equal negative x over y. So there's dy dx. Now I'm going to take the derivative of both sides. The left side we'll see will just come out to be the second derivative. The right side, I'm going to have to use the quotient rule as well as implicit differentiation rules. So like I said, the left side will be the second derivative with respect to x. The right side, we're going to have to do a little bit of work. So using the quotient rule, we're going to take low d high. So that would be the low function times the derivative of the upper minus high d low. So the upper function is negative x. The derivative of the lower function is going to be dy dx all over the low function squared. Okay, so let's clean that up slightly. Just make it a little bit nicer to work with algebraically. That'll be negative y plus x dy dx. Negative y plus x dy dx all over y squared. Okay, so if we want to evaluate the second derivative with respect to x at the point 4, 3, we're going to plug a 4 in everywhere we see an x and a 3 everywhere we see a y. So we would have negative 3 plus 4 times something, we'll talk about that in a moment, over 3 squared. Okay, so what we want to plug in here is dy dx at the point 4, 3. Well, if I look back over to dy dx at the start, that would be negative 4 over a positive 3, so negative 4/3. Okay, so now it's just a matter of simplifying some algebra. That would be negative 3 minus 16/3 all over 9. Now I can kind of see where this is going. It's going to have a denominator of 27. Let's do a little bit more algebra. 3 is 9/3, so that'd be negative 9/3 minus 16/3 over 9, which would come out to equal negative 25 over 27. So the second derivative evaluated at the point 4, 3 comes out to be negative 25/27. Now, they gave us this point, and we should trust them, right? We should trust AP that point satisfies the original equation, but I'm just going to check. So would x squared plus y squared equal 25? Well, that'd be 16 and 9. Does it equal 25? Yes, it does. So this point satisfies the original equation. If the point didn't satisfy the original equation, none of this is valid, right? The second derivative in terms of x and y would be valid, but when I start this process right here, plugging in values for x and y, the second derivative at 4,3 would not be valid if 4,3 didn't satisfy the original. Okay, let's look at number 6. If x squared plus xy equals 10, then when x equals 2, dy dx equals something. We're going to find that something, right? We're going to figure out what dy dx is when x equals 2. So let's go ahead and differentiate the left and right side of the equation given. That would be 2x plus y plus x times dy dx is equal to 0. Okay, I used the product rule on xy. That gave me y plus x dy dx. And I'm going to isolate dy dx, subtracting 2xy and dividing by x. So dy dx is equal to negative 2x minus y all over x. Okay, so it looks like dy dx is dependent on both x and y, but all I'm given is x. So what I need to do is I need to take the original, and if x equals 2, I can then solve for what y equals when x equals 2. So 4 plus 2y is equal to 10. Therefore, 2y is equal to 6. Therefore, y is equal to 3. So we now know that when x equals 2, y equals 3. Therefore, dy dx at the point 2, 3 is going to equal negative 2 times our x value minus our y value all over our x value. All right, I'm using that directly from our solution for dy dx. All right, when I do some math, that's negative 4 minus 3 is negative 7 over 2. Again, our answer is A. Now, it's A only because 2, 3 satisfies the original equation. All right, let's look at another question. All right, let's look at 2008, number 16. No more baby steps here. I'm just going to start hammering this out, so you can pause the video and then come back and check your work if you'd like. All right, so the derivative of sine of xy will be cosine of xy times the derivative of xy with respect to x, which will be y plus x times dy dx. Derivative of the right side, derivative of x with respect to x will be 1. Okay, I'm going to distribute cosine of xy to both of those terms. So I'll have y cosine of xy plus x cosine of xy dy dx equal to 1. Therefore, I will subtract y cosine xy and divide by x cosine xy, and I get dy dx equals the following. Looks like our answer in this case ends up being D as in delta. All right, that took no time. All right, let's look at a couple more problems here. All right, back to 04. This is part of an FRQ. It says consider the curve given. We've got x squared plus 4y squared equals 7 plus 3xy. Part A, show that dy dx equals that. Now, I'm not going to do part A. I want you to verify that on your own. What I want to do is I want to get into part B. So part A will say that we verified it. Okay, for you, that means you need to do that. Okay. Part B, show that there's a point P with x coordinate 3 at which the line tangent to the curve at P is horizontal. Find the y coordinate. All right, so P is going to be this point. P is going to be the point 3, comma, y, right? We're going to find that y value at which the line tangent to the curve. So if the line tangent to the curve at P is horizontal, what that means is dy dx at this point, whatever this point is, right? I don't know the y value yet, but I do know that it equals 0. All right, horizontal means the tangent line at that point is 0. Has a slope of 0, I should specify. Okay, so part B. Let's see how we're going to go about this. So if dy dx equals 0, then that means that 3y minus 2x over 8y minus 3x should equal 0 when x equals 3. Okay, so let's plug in an x equals 3 here. So this would be 3y minus 2 times 3 over 8y minus 3 times 3. We want that to equal 0. Now, in order for this to equal 0, we just want the numerator to equal 0. Right? We don't want to get an expression of 0 over 0, which in this case actually we can't get. But the only way that this can equal 0 is if the numerator equals 0. So now we can find our y value such that the tangent line to the curve at point P is horizontal. Again, horizontal, meaning that dy dx equals 0. So let's solve for y. It looks like y would equal 2. Let's be very specific here. dy dx at the point 3, 2 is equal to 0. This is, in math language, this is saying the same thing as the curve has a horizontal tangent line at the point 3, 2. Those two things mean the exact same thing. All right, so this and our expression written out here, or our sentence written out there, mean the exact same thing. All right, let's take a look at part C. It says find the second derivative at point P found in part B. Does the curve have a local maximum, local minimum, or neither at point P? Now, these questions here that are being asked, local maximum, minimum, or neither, we have not studied yet. So all we're going to do here in part C is actually find the second derivative. All right, so let's take what we know in part B. And let's find the second derivative. So dy dx is equal to 3y minus 2x over 8y minus 3x. So if I took the derivative of both sides, the derivative of the first derivative gives me the second derivative. Now I've got some work to do here using the quotient rule. So I'm going to take low d high, so that'll be 8y minus 3x, which is low, times the derivative of the high function. Well, that'll be the derivative of 3y, which is 3 dy dx, okay, minus the derivative of 2x, which is 2. Okay, so that's low d high minus high d low, which is 3y minus 2x. There's our upper function, times the derivative of the lower function, which will be 8 times dy dx minus 3. And that'll be all over 8y minus 3x quantity squared. All right, so let's do a little work on simplifying the numerator. Though you could be done at this point when it comes to making calculations, you don't need to simplify. But let's go ahead and clean that up a tad. I really don't want to, actually. So let's do this. Let's not do that. Let's evaluate and just find what the second derivative would be at point P. Now, we can't take this information further, so all we can really do at this point is find a value. So I'm going to take 8y. Well, 8 times 2 is 16. 16 minus 3 times 3 is 9, so that'll be 7 squared. Okay, so I'll get all of this over 49. 8y, again, is going to be minus 3x. It's going to be the exact same, so that'll be 7. Okay, times 3 times dy dx. Well, we got to find dy dx at the point 3, 2. So dy dx, of course, was 3y minus 2x. Well, 3 times y is 6 minus 2 times x is 0. Excuse me, 2 times 3 is 6. So you get a 0 over 8 times y, which is 16, minus 9, which is 7. So dy dx will equal 0. This will be 3 times 0 minus 2 minus 3y minus 2x, which came out to be 0, times 8 times dy dx, which was also 0, minus 3. Okay, so what we're going to end up getting is this first term comes out to be negative 14. We're going to be subtracting the second term, which comes out to be 0. So it looks like the second derivative located at 3, 2 comes out to be negative 2 over 7. That's what that value would end up equaling. And I'm not going to go into the details of that, but that's what the second derivative with respect to x at the ordered pair 3, 2 would end up equaling. All right, so I've got my second derivative, which I could leave just like this, and my second derivative evaluated at 3, 2. So that'll be it for this question. Let's look at one more FRQ here on the next page. Okay, example number, this one, 2000 FRQ number 5. Part A, we're just going to assume that we verified. Okay, part B, let's dig into part B. It says find all points on the curve whose x-coordinate is 1. Okay, whose x-coordinate is 1. And write an equation for the tangent line at each of these points. So I'm going to make the assumption that there are multiple values for y. So this is obviously not going to be a function, seeing that an input of 1 yields more than one output for y. Now there could be a third, I don't know, but let's go ahead and figure out what these two y values would be. So if x equals 1, what I can do is I can take my original equation. All right, that'd be 1 times y squared minus 1 cubed times y is equal to 6. Now I'm going to solve this for y. It's going to give me two possible values. So that'd be y squared minus y minus 6 is equal to 0. Now I can factor this. And these will be the two y values that are outputs when x equals 1 on that curve. So I would have y minus 3 and a y, how about plus 2? Okay, therefore, this whole thing will equal 0 when either y minus 3 equals 0 or y plus 2 equals 0. So we're going to get two y values, y equals 3 and y equals negative 2. Okay, so to answer the question, find all points on the curve whose x-coordinate is 1. Okay, our 2 points, in this case, are 1 comma negative 2 and 1 comma positive 3. Now it says to write an equation for the tangent line at each of these points. Okay, so let's take this point and find the slopes at those points. That means I want dy dx located at 1, negative 2. That'll be my slope there. And I want dy dx located at 1 comma 3. Now I'm going to go back to what I verified in part A, and I'm going to plug in those values for x, for x and y into that derivative function. Okay, so let's analyze that real quick. If we take 1, negative 2 and plug values in, that'd be 3 times 1 squared, which is 1 times a negative 2 minus a negative 2 squared all over 2 times 1 times negative 2 minus 1 cubed. So the slope at the point 1, negative 2 on this curve is going to be negative 6 minus 4, which is negative 10. Negative 10 over a negative 5 is a positive 2. Okay, let's do the same thing for the point 1, 3. That'll be 3 times 1 squared times 3 minus 3 squared all over 2 times 1 times 3 minus 1 cubed. So the slope on the curve, or the slope at 1, 3 of the tangent line on that curve will be equal to 0 over 6 minus 1, which is 5. Okay, which clearly would then be 0. So let's write tangent line equations for both of these points. So the tangent line to the curve at 1, negative 2 will be y minus a negative 2, slope of 2, x minus 1. All right, I got the negative 2 and 1 from the original point, and I got the positive 2 from the slope that was yielded from the derivative function. Okay, the tangent to the curve at 1, 3 is going to be relatively simple. That'll be y minus 3 is equal to 0, x minus 1. Now that can simplify to y equals 3, just a horizontal line. So those are our two tangent lines to the points on the curve where x equals 1. Okay, part C says find the x-coordinate of each point on the curve where the tangent line is vertical. Let's analyze this real quick. So the tangent line will be vertical where the derivative dy dx does not exist, right? And that would not exist when the denominator equals 0 and the numerator does not equal 0, right? So dy dx for a vertical tangent line would be where dy dx doesn't exist. That's where 3x squared y minus y squared is not equal to 0, and the denominator, 2xy minus x cubed, is equal to 0. So I want to solve this to find my x-coordinates of the points where the tangent line is vertical. So let's do that. All right, so I'm going to take, for part C, 2xy minus x cubed and set it equal to 0. I want to know what values will give me 0 there. Now I can factor out an x, which leaves me with 2y minus x squared. Okay, what that tells me is that for this product of two values, x and 2y minus x squared, for this to equal 0, either x equals 0 or 2y minus x squared equals 0. Now, if x equals 0, let's see what happens. Let's go back up to the original function. Okay, let's plug in a 0 for x. So if I plug in a 0 for x, I get 0 times y squared minus 0 cubed times y is equal to 6. Now that would mean that 0 minus 0, or that 0 equals 6. Is that ever true? That is never true. Therefore, x equals 0 is not a solution. Okay, so if that's not a solution, then that means there is no vertical tangent line x equals 0. Okay, this is what's called an extraneous solution. You've seen these. An extraneous solution. You saw those in pre-calculus. Okay, so beware. That's fool's gold right there. Let's work the other side of things. Okay, so let's solve for y here. Well, y would equal x squared over 2. So when y equals x squared over 2, the denominator of our derivative function is equal to 0. So let's take our original function, which was, and it wasn't a function, our original equation, xy squared minus x cubed y, xy squared minus x cubed y, set it equal to 6. And what we're going to do is we're going to plug in an x squared over 2 everywhere we see a y. Okay, so let's plug that in there. X squared over 2, x squared over 2. And I think I messed something up here. This is x cubed. There we go. Okay, let's solve for the x value for which this is satisfied. All right, and then we'll end up finding ourselves a y value if necessary. All right, so that would mean I'd have x to the first times x to the fourth over 4 minus, this would end up being, I guess I could just leave it in this form, x cubed times x squared over 2. Okay, so that would be x to the fifth over 4 minus x to the fifth over 2 is equal to 6. All right, so what that means for us is then we have x to the fifth minus 4, over 4 minus 2x to the fifth over 4 is equal to 6. Thus, if I subtract 1x to the fifth over 4 minus 2x to the fifth over 4, I get negative x to the fifth over 4 is equal to 6. Now, what does this mean? Whatever x value is yielded is a location determines that dy dx at this x value does not exist. All right, it's vertical. It's a vertical tangent line at this x value. So I'm going to quick work out the algebra here. This would mean that x to the fifth is equal to negative 24. And now I can take an odd root of a negative number. So this would be the fifth root of negative 24. So x at the fifth root of negative 24 has a vertical tangent line. All right, so just to review, please don't be fooled by the fool's gold of x equals 0. That looks like a nice answer, but when we plug it back into the original relation at the very beginning, it's not a solution. Therefore, finding the slope of the tangent line at that point is not valid. All right, that's it for today. We'll see you guys in the next video.